Okay, so Tamara, I'm gonna try using the headphones with the speaker since it didn't look like this computer speaker was working very well the first hour, and I am more than happy to set up a Zoom meeting with you to go through the assignments if you missed any of that. One thing we did say is that the intro module does not reflect all the current assignments, so we should touch base if you're confused by that. And so the next thing we have that we're going to do today is just this little bit of stats review. So I'm going to jump into that, and feel free to stop me at any point along the way. And I think I will try to pull this up. So Paul Cook, who many of you have met before, was the director of our Office of Research and Scholarship a number of years ago, and he developed a lot of those materials that are in that virtual CNRS that I just showed you, and he has also contributed a lot to these slides. So I just want to acknowledge and thank him for the contributions he's made to this course because they're enormous. So let's jump in and just talk a little bit about science and then how statistics helps us with quantitative science. So if we talk about three possible goals: describing the world around us. So that involves more descriptive statistics. Now, describing the world around us might be qualitative and involve narrative as well. But from a quant perspective, when we're talking about describing the world, it's just describing what's out there. And as we'll talk about later in the week, what we do with quantitative science is try to kind of build. So you want to know what we currently know, and that's why you review all the literature. And then you want to push it one step further. So if we don't know anything about a problem, a condition, an intervention, if we don't know anything about this particular issue, you usually want to start with describing it. What do we know about this? And just describe it. And then people can then say, okay, is this what I'm experiencing typical or is it unusual? So can you think of a type of descriptive quantitative study? What would we be talking about? Absolutely, and this is why quantitative is important to a qualitative researcher. Even if what you're going to be doing is qualitative, you still want to give what they say in qualitative science is a thick description of the sample, so people know whether or not your findings will apply to their population. So that's descriptive statistics. Who are these people? What are the characteristics that I need to know about them that may be different or the same as my population? Can you think of anything else that would be a descriptive study? Mm-hmm. 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 Yeah. just describing that population or describing a new problem. So a number of years ago, we started seeing all this stuff about the Zika virus. And the Zika virus was new to most of us. So you're not going to start with an intervention. You're going to start with a description. Who does it affect? So we found out it had terrible consequences to some pregnant women, but not all pregnant women. Do we know? Is there a vulnerable time in pregnancy? Is there some predisposition? So it started with just describing how this new disease looked. So that's a descriptive study that you're starting with something brand new that we don't know anything about. So descriptive might be where the state of the science is around something like that. Can you think of any others? Yeah. So if we're just describing what this problem looks like in another country, then it would be descriptive. If we want to if we want to compare, I heard you say in the beginning of your statement, comparing the United States with another country, that takes us to a different type of quantitative design. So compare means I'm going to look for differences. That's a different analysis, but that's a really good example of how we could just describe the population, the problem in another country, or we could compare. And the way you approach those two methodologically would be very different, and the way you would analyze them would be different. But both of those would be quantitative. So if the work hasn't been done where you compare the issue in that country, maybe that's where you start. Or, I mean, if it hasn't been described, you start with the descriptive. But if they've described it and we've described it, then the next logical step would be let's compare these two and maybe even explore what the interventions are in the two to better understand the differences. So that's a good comment. The other thing we can do is predict. So predicting the future, it can be, so I'm working with a group of nurses, well, it's an interdisciplinary team in the Cancer Survivor Clinic at Children's right now. And what the literature is pretty full of right now is that we know kids who have completed cancer treatment have a much higher incidence of being overweight or obese. So there's been a number of publications with a number of different types of cancer, with a number of different types of treatment, with different ages, different populations. So what we're currently doing is seeing if we can predict what are the strongest predictors of kids ending up overweight or obese after having a childhood cancer. So we're looking at the age, we're looking at their pre-cancer weight, we're looking at race, ethnicity, we're looking at what kind of cancer they had, what kind of treatment they had. We know that kids who have cranial irradiation to the pituitary, that's, that has an impact on growth, but some people have hypothesized a variety of different explanations for this, but what we're currently doing is trying to see if we can see what's the strongest predictor. So that's an example of a predictive study. And then if you want to control, you can look at the cause and effect. So cause and effect, what's the best intervention, what's the best treatment, what's the strongest counseling to get patients to adhere to treatment. Those are all things that are more true experimental design if we have both a treatment and a control. So there's a variety of questions that you can answer with quantitative design, and your methods and your analysis will be different with each of those. Yeah, that's a really good question. So the psychometrics around an instrument sort of fall in between that descriptive and predictive, I think. So you're using that instrument to say, you will want to validate it. So you will want to say, can I predict how good this measure is at capturing what I want to capture? So it's kind of in that in between kind of area there. But reliability and validity, the psychometrics of an instrument, that's another important area. That's a good example. I mean, that's a good comment too. If what you're doing is comparing it to a gold standard, then it is comparative. Absolutely. Absolutely. If what you're doing is face validity and you're having experts comment on it, it's almost a little qualitative approach, right? So it depends on what methods you're doing to establish the reliability and validity. Yeah, but no, that's a really good comment. So what are good statistics? The things that we think about are how big, how much, how many. So those are the descriptive statistics. And that also includes an effect size. What is an effect size? Anybody remember? Yeah, so we want to know how big of a sample we need to get an effect size that would be meaningful at a 0.05 or a 0.01. But what does the actual effect size refer to? If I say I have a large effect size, what am I saying I have? I have an adequate sample to do what? A more powerful statistic to say that these findings are more than by chance. So it helps you make some predictions. So it could be a correlation if that's what we're talking about, or it could be suggests there might be a difference. If you have an effect size, a high effect size, it suggests that you might have a good intervention that should be tested further. And then we also use statistics to answer the question, how likely? So those are inferential statistics. They tell you whether your finding is reliable and not due to just chance. So the graphic on the bottom tells you if you roll dice, it's you have 14 different possibilities. Heads or tails, it's either yes or no, heads or tails. So it's a 50-50 chance, and the sun will rise tomorrow, we hope. So there's a pretty good chance based on, how many ever billions of years that's been happening. We know there's a pretty good chance that's going to happen. Does that make sense? So what are the types of data? If we talk about nominal, we're talking about groups or categories. So there's number of boys and girls, number of fifth graders in a class. The graphic talks about vanilla, chocolate, and strawberry. Those are nominal. So we're just going to count up how many. And then you have ordinal, which is maybe an example as a class rank, or this graphic here is nominal, so strongly agree, agree, disagree, strongly disagree. That gives you a rank order. Now, it doesn't tell me if my answer between strongly agree and agree is the same distance as agree and disagree, right? It just tells me they're in order. It doesn't tell me the distance. So that's important to remember, that ordinal doesn't mean that there's equal distance between the different levels. Interval or ratio has those values on a scale where you have a little more chance of things being equal distance if it's an equal interval. And ratio means what? Anybody remember what ratio, what the requirements are? Yeah, there's an absolute zero. So your statistics that you can do based on the type of data varies. Remember, there's parametric and non-parametric. So if you have nominal data or data that's not normally distributed, you're going to go with the non-parametric approach. If you have interval or ratio, you can use the and a normal distribution. You can use the parametric. So you want to use the highest level of data possible to collect and the highest level of analysis that's possible, just because it makes your results more credible. But sometimes, sometimes you can't. There are some things that are only categorical, the males and females. That's just the way it is. So you're going to be answering two questions. The descriptive statistics tell you how big, and those are things like the Cohen's D and the Pearson's R and the odds ratio. And the inferential statistics tell you how likely. They can't tell you how big, and they can't tell you how important. The tricky part when you're interpreting is it's based on that double negative, right? So your hypothesis is about a negative statement, rejecting the null, which, as you're writing up these analysis assignments, you want to keep that in mind. So here's just an example of weather, temperatures in New York in 2003 throughout the 12 months. And you can look at this and you can predict what kind of temperature you should expect in mid-July in New York. So here you go. Here it is. There's a range. What is that? I can't see here. Looks like 80-ish. And then, has it ever been 100 degrees in New York in April? So you can look and see that it's been up to 90, but it doesn't look like 100 in this particular year. And then, should I bring my heavy scarf to New York when I go there for Christmas? And you can look over here and see, well, it's chilly. And then the gray shaded areas are kind of your range, right? So it's possible, like back to the question of 100 in New York in April, looks like it got above 90, but doesn't look like 100. So you can use those kind of data to sort of answer those kinds of questions. So somebody mentioned when we were talking earlier about descriptive statistics, what do we get? So we get the mean, and everybody knows the mean is your average, right? You take everybody's score, you add it up, you divide by the number of people, and that's the mean. So what messes up a mean? Yeah, if you have a real high or real low number in the mix. It messes it up. And in those cases, the median is the value in the middle, and that might be a little more reflective of the actual population, depending on what your outliers look like. And then the mode is the most frequently occurring. So you can see in this example, here's the mode, here's the median, and did they get, oh, and here's your mean, the average. So they're very different numbers depending on what you really want to be asking. And sometimes you report all three of those because people may be interested in different aspects of that. But those are examples of descriptive statistics. So in this particular case, the boss is the outlier. His salary is different than other people. Oops, did I get all those? Yeah. So the mean and the median are not always the same, and the more skewed the data are, and skewed just means you've got outliers on one end or the other. The more skewed the data, the less likely they are to be close to each other. And the more error there are in the data, either randomness or complicated patterns, the less the average will describe the actual results. So again, if we look back to this one, you know, our outlier here really influenced. So the mean is 5,700, but there's all these people that are below that, and there's very few people above it. So that just helps you sort of visualize the problem with going with the mean. So when we're asking the question, how big, there's a variety of statistical tests that we can do depending on what design we use. So correlation is one of those who can tell us how big, and it's how big is this relationship between these two things. So a 0 is no relationship, 1 is a one-to-one correlation is a positive relationship between those two. So as I go up one step in one variable, I'll go up one step in the other variable. And a positive correlation means there may be an effect, and a negative means no effect. So 0.3, and Paul likes to tell the story of Cohen, who says when he was pushed to say, so what do these data mean? What's a good number for a correlation? He said, it depends, and I won't give you a number. And so people establish these. So people say a 0.3 is small, 0.5 is medium, 0.7 is large, and Cohen says, don't go there, it's not safe. But these are pretty widely accepted for small, medium, and large effect. The R square is the percent of variability accounted for in that statistic. Now the Cohen's D gives you some information on the means and how those standard deviations fit into that. So how far apart are the means of two groups from each other? And that's a 0 is no effect, a 0.5 is a small effect, 0.75 medium, and 1 for large. Odds ratio is another way to look at how big this relationship is. So you can get a 1 means no relationship, less than 1 means there's a negative effect, and over 1 is a positive effect. So, and then the other important thing to know, and this will come in really handy for you to remember when you do the meta-analysis assignment, is that all the effect size statistics are interchangeable. So when we're talking about a meta-analysis, anybody know what that is? Have you read a meta-analysis? Have you come across it? What are those? Yeah, so synthesizing, just like you did in your qualitative synthesis, you're going to synthesize a number of studies done with the quantitative methods. And it's absolutely possible, even if they did different methods and different analysis, because these effect sizes are interchangeable. And that's what that meta-analysis calculation sheet will do for you. So when you're reading the studies, first of all, they have to measure the same thing, and then they have to report an effect size or give you, give you enough information to calculate an effect size. And then you can plug those in and synthesize. So let's say we have a study with a sample size of 20 and they have a strong effect size, but we have a sample size of 250 and they have a small effect size. And we're looking at these two studies and you go, what do I believe? Meta-analysis is a way that you can convert those and combine them to help you come up with what to believe about those studies. And that's why when you're searching the literature and you find a meta-analysis on your topic of interest, somebody's done that synthesis for you. Somebody's combined those and helped make meaning out of those multiple studies. So snag those articles if you run across them. Where's a good place to find them? Any Cochrane Review. Another good place to find synthesis is the Evidence-Based Practice Journal, Worldviews, has a lot of those kinds of reviews. Worldviews, yeah. So, yes, yeah. The Joanna Briggs Institute is another source, the Cochrane Library. But anytime you see a meta-analysis, somebody's done that work for you of combining the findings of multiple studies on a similar area. So another really important thing to keep in mind when you're thinking about quantitative research is to say there's a correlation between two things does not mean that one caused the other. So Y could influence X, and the example is sleeping poorly and lack of focus. So does lack of focus make you sleep poorly? Probably not, but the sleeping poorly can lead to lack of focus. So the correlation, but yeah, yeah. So, so then there's that second bullet. There could be a third variable that affects both X and Y. And the example there is ice cream sales and the number of fist fights both go up in the summer. So, so it's the temperature that has the relationship on both of those. There could be an indirect relationship. So past success influences positive expectations and more success. Or it could be just an accidental relationship, sunspots and the Dow Jones Industrial Average. Probably there's not a cause-effect relationship there. So the other concept that you have to keep in mind that makes all this a little bit tricky is the variability. And when we look at variability, it's looks like we lost part of the words here. It's not what's the average, but what differences are there from that average? Is it something else? And you look for the overall pattern. So a good example of this is, you know, your money in the stock market. It goes up and down. It has a lot of variability. We sometimes have some pretty significant dips and then it takes a while. But in general, over time, it goes up. And so you have to look at variability being a part of what you measure. And then certainly 1929 and again in 2008, there were those significant dips that made all of us anxious. But overall, the money that you put in the stock market goes up over time. The variability shows this different pattern. There can be a depression or a recession in the economy, and those are those dips. Another concept for us to just keep in mind is the mean absolute deviation. So as we look at these variables along this continuum of heights, you can see the pink are for the girls and the blue are for the boys. And as you look at this, the average is 55 inches. But is the average girl 55 inches? Or is the average boy 55 inches? And actually, it would be different for the two. And you can see the deviation. I can't really see the bottom here very well. So you calculate a deviation for each person, find the absolute value, add them up, divide by the number of people, and that gives you your mean absolute deviation. So it's just a way to combine that data and really look at the differences. And let's see if I can find the next. So compared to the range is 23 inches, but your mean absolute deviation is 4.9. I'm sorry? Yes, that's including the outliers. And that's a really good question as well, because there might be occasions in your data where you look at it and you say, that's just not possible. That's a mistake. And especially I do research with children and some self-report instruments, and some of what they put on them, they're just messing with you. And if we even use this data, what if we said these were adolescents that we were doing height and that outlier was 22 inches? Well, that's clearly an error. It's impossible. So when you're cleaning your data, that outlier would be removed. But in that particular case, it included the outlier. That's a very good question. So the peaks of the distribution are not the average value. And as you look at this data, you see that there are really two levels. And as we mentioned, the pink dots are the girls and the blue dots are the boys, and you can see that it's bimodal. So you have here and here. And if we analyze this for boys and girls, it would be very different. The average would be very different for those. And we know that's true, that typically boys are taller. So the average for girls was 53 inches, and the average for boys is 59 inches. So that's much more meaningful data when you're, especially if we were looking at, adolescent or adult heights. It would be sort of absurd to say your average male was 55 inches when we know that's really not the case. So it depends on what the question is. So when you have two peaks in your data, there are probably two underlying distributions, and you want to look for that moderator variable. And in this case, it was easy. It was male and female. But when you're looking at your data, it might not be that easy, and you might have to really give it some thought. Like, what is the explanation for these two peaks? Is there a different variable here that could be explaining it? Can you think of any examples? That's a really good example. That's a really good example. Because I'm a peds person, I can give another example. So one thing we've noticed in child development, in language development, in kids who are in bilingual homes, their language development is slower. They're not saying as many words as they're learning both languages. They eventually catch up, but when you're talking about a toddler learning two languages at once has fewer words at two. Um, so people get upset about that, want to send them off to speech therapy or whatever. They're totally fine. It's just that the difference is they're learning two at once, and so their verbal expression is a little bit slower. But your example is a perfect example too. So think about that when you're looking at your data. Is there something that would explain it? And as you design your studies, it's good to think about and you're reviewing the literature, what are the possible moderator variables that I should be measuring that could help explain any differences that I'm going to see in this data? So the other thing that you can do with looking at the data and the descriptives are just looking at box plots. And these are two examples of some box plots. And it's just the number of hot dogs eaten and the number of contestants. And there's the same data it represented two different ways. And you'll want to look at your data and decide which one is more meaningful. The good thing about SPSS is you can click and it'll give you both of these. And as you're reviewing your data, it might be really helpful to look at it both ways and say which one helps me tell the better story about this particular study. Absolutely. Yep, absolutely. And your book does a really good example of describing these and giving you some really practical kind of healthcare studies to put numbers to these things and help you look at presenting it different ways. So these are the same data that you'll see in the bar graph and the stem and leaf format. It's just presenting the data in a little bit different way. Oh, and down here on the bottom, which I didn't really point out here, this is also another way to present the data. So here is your mean, and here's your median, your mode, and here is the standard deviation. So it can go all the way. And that's just one other way to present the data. And as you're reading the articles, pay attention to how they present. What did they tell you about the population, the analysis, and then how did they present it? And how did they present their standard deviation? All right, let's see if we can go. Then meta-analyses will frequently use these box plots to help you compare the studies. And this particular one is presenting the shoulder measurements in these various groups. So you have the gorilla, the chimpanzee, the orangutan, gibbon, and the human, and you can see that that humans are more similar to gorillas from looking at this. But look at these are the standard deviations, and then there's your mean. So, as we said, humans look most like gorillas, but we have less diversity as a species, and most of the variability is in the upper end right here. This one is the dot plot describing relationships. So you just put each score on the plot each score for each individual, and it sort of gives you a shape. So what would you say about the correlation between education and the child's health? Oops, I went up in this one. Yeah, and it says a moderate correlation with an R of 0.5. But it's because they tend, it's trending up. What do you say about this one? That one's just a little weaker because it's kind of scattered all over. And then this one's stronger yet. So those are things that you can also use to describe the relationships. And you can do analysis then that helps you predict how far from the line and helps you calculate those relationships. And one of the assignments that we'll do in this class is looking for that goodness of fit. So how well does this line describe those data? And a 0 is no relationship, 1 is, you know, a kind of perfect relationship. And as we said before, 0.3 is small, 0.5 is medium, 0.7 is large. So I think this is a good place for us to pause for a second, give you another, just a little break, and we'll start back in 10 minutes. Okay, so there was a good question at the break. Let me see if I can go back. So a good question at the break, I think I pointed out when you do meta-analysis, many times they present these in the box and whisker plots. And Jenny's reviewing an article which did exactly that thing, reporting their data with these box and whiskers. So let's just talk about what these lines are. This is the lowest score. This is the highest score. So that's what those whiskers tell you, highest and lowest. This is the 25th percentile. This is the 50th percentile, or the median. That's the middle point. And then this is the 75th percentile. Oh, and it's not showing up on there. I'm sorry? Yes, yes. So that helps you just make some meaning of what those box and whiskers are. This is the same data with the bar graph, and then your stem and leaf. And it just depends on what is the easiest way for your reader and for you to make sense of it. But many times with the meta-analysis, you can put a lot of different studies up together. And I think, is that a meta-analysis you're reviewing, or is it just different measures? They did it with different measures. Many times they'll do it with a meta-analysis with looking at the variables of interest or the interventions of interest, and summarize those. And you can get a lot of information if you use these box and whiskers, because that only takes up a small amount of time to summarize everything. Versus these two take up a lot more space. But it depends on what you're trying to do. Yeah, go ahead. So those are the interquartile ratios, and again, all of that is described in calculations in the Monroe book for you. But in reality, SPSS does the work for you and gives you the little results. And for the purpose of this class, I don't want you to memorize formulas or do any math calculations. That's why you bought SPSS. And in reality, it's good to understand the concepts and know that it's based on some mathematical formulas. But if you can come up with do the analysis with the software and interpret the findings, that's all you need for this course. But that was a good question, so I thought we'd go back to that. So let's go back to where we were. So why do we care so much about this variability? There's a variety of different explanations for why this variability matters, but one of them that's become a recent sort of thing that we're spending more energy around is heart rate variability. And what the data is suggesting is that heart rate variability is better than blood pressure in predicting heart attacks. And we also know extreme events like storms and earthquakes can't be predicted by the average. So this understanding this error is important. And when we're looking at different patterns, this is a good example of how likely is likely. If you plot the findings for these individuals over time, you can see there's a whole lot of variability. Look at how this person goes way here to way down here, way up here. It's just crazy, the variability, and sometimes that's really important in helping us understand what the data mean. So each line in this graph is an individual baseball player's batting average by the age. And you can see that over time it declines. And here it's kind of peaking for everybody. But look at the variability. So that's just important as we're trying to understand some of these data. There's the overall curve, but you still have these people here and these people here. So it can give you the average at age 29, but it's really not giving you the full picture. So the variability is really important. And the blue line is the overall pattern, but no individual player really fit that exact line. So that, again, just helps you understand where the variability plays in all this. So statistically significant, or a p-value of less than 0.05, means that it's not just noise, that it really is the best predictor or the best bet of peak performance. And a correlation tells you how noisy the data are. They're close to zero, or they're typical, or good, or great. So if we want to look at how likely we can use a test statistic that looks at the means between two groups, but takes into consideration all this noise, or the additional influences on those two means. So that's what we look at when we remember our regular distribution here. So when we are looking at a normal curve, we know that here's your mean, here's one standard deviation, two standard deviations, three standard deviations, and we know that the majority of the scores are going to fall within two standard deviations, and that's how much of our statistics are determined. So when we say the 0.05, it's taking that we're going to capture people in this part of the curve. So another thing that that you want to keep in mind is usually you want to use this two-tailed curve unless there's a compelling reason that you can predict which direction this is going to go. You really want to use the two-tailed test. So when we start looking at differences between means, when you go to SPSS, you're going to tell it one tail or two tail. So if we say, let's see, if we feel like there's enough data to suggest that we know there's only one direction this relationship can go, then it would be a one-tailed test. But in general, the strongest way to approach analysis is to use the two-tailed, accepting that the data could go either way. So when you're doing hypothesis testing, you really think about 5 steps. You're going to state the null and the alternative hypothesis, calculate a test statistic, and find the corresponding p-value, and then you'll reject or fail to reject the null. And then you draw your conclusions. So can you come up with a null hypothesis and an alternative hypothesis? Okay, or there is a difference between, you know, another possibility. No, it's either there is a difference or there isn't a difference. So, yeah, that's a good question. Good question. Right. Right. So an example of that would be, you know, drug studies. We have a lot of studies done on different drugs before they hit the market. And so you could say, let's say, um, treating Tylenol or treating a fever with Tylenol will decrease the temperature. We have pretty good evidence that that is the case. So you wouldn't say it'll raise the temperature because we have good evidence, unless you, of course, you do an overdose, and then sometimes you do. But so there's an example of how you have enough evidence to suggest. But yeah, and Paul has a really, really strong statistics background, and he says you just never go two-tail. You will never be critiqued for it's the more conservative approach to use the two-tail, and if you find significance using the two-tail, no one will be able to critique you for cheating and going the one-tail approach. So it's just probably the better way to go. What's that? He says always use a two-tail. I don't know what I said. Always use a two-tail. Yeah, don't let me misquote him. Yeah, the conservative approach is two-tail. You'll never be critiqued for doing it inaccurately. And yes, there are some logical reasons where you have enough evidence to suggest a direction, but probably better to always go with the two-tail. So now let's talk about some of these other statistics. Back here a ways, we saw the z-score. And see, the z-score down here is telling you about the distance from the mean, those standard deviations. So you can see that on the bottom there. And a large z-score equals a large effect, which is also sometimes a D and a low P. So it means that it's a significant effect usually. A Z depends on the sample size and a D does not. So every test statistic is the product of the effect size and the sample size. And again, when you're trying to do these meta-analyses, sometimes they report an R, sometimes they report a D, sometimes they give you the sample size and the D and the p-value. And that's why that meta-analysis calculator is going to come in handy, because you will be able to combine those and convert them to a common score and then be able to come up with an overall synthesis. So a significant result of your power depends on what alpha you choose, how large the effect, which is your D, and your sample size. All of those need to go into the equation in order to tell you how meaningful your findings are. Well, I'm hoping it becomes clear to you in the reading what that means. You are not going to, you're not going to do the calculations. I guess I'm not sure what your question is. It definitely is covered in more detail as we go through. Let's talk about what type of test now. If you're going to look at a difference between two groups, you're going to use usually the t-test or the z-test. And this is also covered in the various chapters in your reading. And we do one at a time. But in general, if you're looking for a difference between two groups, you're going to use a t-test or a z-test. If you have three groups, you're going to use the ANOVA. And if you're trying to do correlation or regression, you're looking at interval or ratio level data. Correlation answers the question of how big, but you can't convert it to a t-test because what does the t-test tell you? Correlation says how big is this relationship? What does the t-test tell you? Difference. T-test and z-test are telling you difference. Now the F test is the ANOVA, and that's analysis of variance. And again, SPSS does this for you and gives you the statistic. What it does is compares the variability between two groups and tells you the between group and the within group. So it helps you differentiate that signal and noise. Remember that we were talking about. So this is, and again, this is in great detail in the Monroe book with a little more explanation. But when we're looking at the F statistic, it also gives you the correlation, and it's going to help you with the understanding of the between group differences and the within group. So here's the regression and the F test. And again, just eyeballing this, what would you say about the relationship between these two variables? Yep. And there's the line of the best fit, which minimizes the sum of the squared residual, so it helps you predict, make meaning of all those individual dots, that this is a strong relationship. And it's that mathematical calculation, but this is the picture. So there's your predictive value, which you see is not even a dot on there, but it helps you put a actual numeric value to it. There's the actual value, and there's the error variance. There's your predicted. And again, there's the formula. So what that then requires is that you do some post hoc tests so that you can make some more meaning of it. And the F test compares 3 groups at once. And the benefit is it really avoids that chance. The drawback is you can't really see the individual differences. So then the solution is to do these post hoc tests. And that's things like your Bonferroni or your Tukey. And again, all you're going to do is check those little things in SPSS, and it will provide those data for you. So I think we referred to this a few minutes ago. The parametric tests are require some assumptions. So the normal distribution, the independence of the sample, the homogeneity of the variance, and the linear relationship between the independent variable and the dependent variable. If you have a violation of any of those assumptions, you use the non-parametric. And the alternatives are listed for you there. So either the Mann-Whitney-U, the Kruskal-Wallis, or the chi-square, if you violate any of those assumptions. And again, SPSS is going to tell you whether or not you violate those assumptions. Chi-square is one that we use pretty often. It's a non-parametric test that helps us look for differences between groups. And you sometimes will see the data presented like this in a contingency table. So group 1 has some characteristic absent and present, and group 2 has it absent and present. And then you have the odds ratio listed for you down here, and the risk ratio. Oops, I'm going too fast. So let's go through a couple of those, the assumptions. Independence is a major assumption of the parametric, but not the non-parametric. So if you want to address a non-independence, you can actually collapse some scores to a single observation by looking at a change score. So you might look at the post-test minus the pre-test, and you can calculate the standard deviation of the change score. I think what I'm going to do, since we're down to about a half hour, let me go to I think I'm going to have you look at some of the data real quickly since we're kind of running out of time. So if you guys would sign into Canvas, go to the modules, and go down to this outcomes data recoded. Is it opening it up for you in SPSS? Okay, good. Yeah, mine too. And then it says the license expired, but it still let me in. So has everybody played with this a little bit? As you open it up, you can do the data view or the variable view. So if you look at the variable view, it kind of lets you know what, how your data are put in there. It gives your data a name. It tells you if it's a string or a numeric. It tells you how many decimal places. And if you go over to the second to the last row, it tells you if it's nominal or scale. And you plug that in when you enter your data. That can be really helpful. So how about if you go to the data view, and let's just do some descriptives. Let's go to Analyze, Descriptive. It's not opening? Oh, okay. 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 Let me know when everybody's in. At the bottom here, see where the little orange? Yeah. So I'm in data view right now. Okay. So we're going to go to Analyze up at the top here. And again, if you, what I suggest you do is either have two screens at home when you're doing the analysis assignments, or go to that virtual CNRS and print off the step-by-step instructions of how to do these and have it with you, because it walks you through exactly what you're aiming to do. Either way works. So you're going to go to Descriptive Statistics. And then go to descriptives. Everybody with me? And then you're going to tell it which variables. So let's see what it tells us the ages of this sample. And let's go to, let's see what else we want to do. Let's do, the MAST score, and that's some substance use stuff. And then let's go down. Oh, very good question. So the sum is the last one. and the DAST. And let's just say now go to options. So it'll give you your standard deviation, your minimum, your maximum, and variable list. So we'll hit continue and then OK. Everybody with me? So the age of this population, we have 130 people in the sample, and the minimum age was 18, the maximum age was 70, the mean was 40. And these are substance abuse scales that we did, the MAST and the DAST. And the means were 9 and 10. Now, would you expect there to be a correlation between those two? If they're one's for alcohol, one's for drugs? So let's go back and do that. So analyze, correlate, bivariate, and put in your MAST and your DAST and see what you get. Oops, I may have gone too far. I'm going to ask for the means and the standard deviations as well as those correlations. So there you have your the comparison or the correlation between the two. So 0.488, and its correlation significant at the 0.01 level with a two-tailed test. So absolutely, as we would suspect, there's a good correlation with those two. Now let's see if we can go back and let's see if we can find. I usually you have to plug in how you want to handle the missing data. So I don't know if there's a default. That's a good question. There might be a default. Yeah, I don't think I know the answer to that. Let's go back and look and see if there's a difference in by sex. So we're going to do, let's do a Oops, what did I do with it? Yes. So you're going to run, that's a good question as well. You're going to run this, you're going to cut and paste this along with the description. That and some, yes, and some, well, there's only one assignment that requires the syntax. And it specifically tells you. But what you're going to do is turn in this analysis sheet and your description of what that means. So let's see, let's have you do one more. Let's do a correlation between, let's do age and the mast. I'm sorry? It's just taking them out. Yep, good. So what does this one tell you? But it's not significant, right? Good. And remember the last one that was significant had the asterisk, it flags it for you. And it had 2 asterisks, so it was significant at the 0.01, and 0.05 is acceptable. So yeah. Okay. Questions? Yeah, so I went to general linear model univariate. And again, if you have, there's going to be a voiced PowerPoint that'll walk you through the steps so that you know when you're looking for differences which one you're going to use. But you also can pull up those step-by-step instructions in the virtual CNRS to do the ANOVA and the repeated measures. Because I don't expect you to know all this, and it's pretty intuitive, but it's not called exactly the same things as your assignments. But there are instructions, I promise. Yeah, that's another really good point. There are multiple ways to do it. There are multiple ways to get, I mean, you could do the compare means part too, the t-test and the one-way ANOVA. So that's a really good point. And you can do the GLM. So you can do it multiple ways. That's a really good point. So are you more anxious or less anxious? Okay, we'll try to address that tomorrow. More anxious about what else? Well, it better be on the first floor. Is it open? Oh boy. Okay, you know where building 500 is? You go out our building and go straight over. Yeah. Boy, that seems like criminal. I think they're providing you lunch today, though, right? What? Yeah, that's a hike too. I can't believe it's not open. They were predicting midsummer. And then,